Okay, so welcome back. In our last video, we talked about covalent bonds. And covalent bonds, I'll just jot this down again. And let me make sure that I've got my pen going over here. And go with this color blue here. Just a quick review here. Our covalent bonds are between two nonmetals, right? So two elements to the right of the staircase on the periodic table, and they share electrons. So then what does it mean when we say bond polarity? Let me just go and grab my little clicker here thing. So if I said to you that my brother and I are polar opposites, what does that mean to you? Well, polar, by definition, means different, right? So if we think of something as polarized, it means like extreme or different, right? So I like to remember that this word polar means different. So I'm going to write this over here. So as long as you're thinking that the word polar means different, this is going to help you later on when we talk about the polarity, the difference between the polarity of a bond. And now this is going to be our video on bond polarity. And then in our next set of notes, we're going to talk about molecule polarity because there's a difference between the two. But polarity means different. And in this case, when we're talking about the bond polarity, it describes how valence electrons are shared in a bond between two atoms. And what does that mean? This means two different nonmetals. So for example, hydrogen bromide would be a polar bond because it is two different nonmetals between hydrogen and bromine, which would be the bond between those two. So now what is a polar covalent bond? The electrons are not shared equally, or because the polar word means different. So if I look at here at my image of this chlorine and this hydrogen, this chlorine is like a pretty strong, element, and this hydrogen is a pretty weak element. So if we're sharing electrons, chlorine's stronger. The electrons are really going to be shared closer to chlorine than they are to that hydrogen. So they're not shared equally, because look at how much more those electrons are over here. They're getting pulled closer to that chlorine. So one atom has a higher electronegativity value and hogs the shared electrons. So remember, electronegativity is that value that's listed on table S of your reference table, and it means the attraction for electrons, not elections, electrons. So attraction for electrons, right? So chlorine has a much higher electronegativity than hydrogen does, so it has a stronger pull, which means the electrons are hanging out closer to chlorine than they are to hydrogen. So in our example of hydrogen chloride, I've got the hydrogen, and it has one valence electron. Remember the last electron in the electron configuration. Chlorine has 7 valence electrons. And now they're going to share this pair of electrons between the two. But now remember, one is stronger than the other. Just because they're sharing doesn't mean it's going to be equal. So then when they share these electrons, right, so this is that shared bond between them, right? This is a pair of electrons that gets shared. The chlorine has a stronger pull. So it means like it's getting pulled. All the electrons are getting kind of pulled in that direction. So that's where the pull for the electrons are. So we end up with one slide that is slightly positive. This is our lowercase Greek letter delta. And to make a delta, it just, to me, it looks like an incomplete 8, right? So I start making an 8 and stop. That's a delta. It's not a full positive charge. So that means this is a partial positive. So we've got a partial positive over here. If it was a full charge, it would be an ion. So this is not an ion, this is a partial positive charge. So let me just move this. I want to move this up over here. So it's just a little bit out of my way. Okay. And then we have our partial negative charge. Because the electrons are kind of hanging out over here closer to chlorine, so you've got more negative charge on that part of the molecule. So it makes it like a little bit of a magnet. So chlorine's electronegativity value, and again, right from table S of your reference tables, is 3.2. So that means on a scale of 0 to 4.0, chlorine's got a 3.2 in terms of its attraction for electrons. Our electron's going to be going towards that element. Hydrogen's electron attractive scale is 2.1. So the electronegativity difference is 1.1. Right? That is going to be our electronegativity difference. So then that's going to tell you how polar, right? So how different, right? And when we do difference, that means we subtract, right? So you need to subtract the electronegativities in order to figure out which one would be most polar, least polar, or to figure out whether or not it's polar at all. So now what is a non-polar covalent bond? So if I say that the word polar means different, if I put a non in front of it, it negates it. So not different. So when I say something is not different, that means the same. So here I have two of, not same, same, oops, same. Two hydrogens are the same exact element. If they're sharing electrons, they're both going to be equally strong because they're the same element, right? Identical twins, right? Pulling in this direction and pulling in that direction, it's going to be equal. It's going to be an equal pull, not different. So the electrons are shared equally in the bond because there's no difference in electronegativity, which is your attraction for electrons. So atoms have the same or similar electronegativity values. And again, where do we find these values? Right, we're going to find those values on table S. It's a 0 to 4.0 scale. So if I look at hydrogen, hydrogen, right, so not different, the same. So these are going to be electron shares equally in a bond. And I just want to write in here between two of the same and then non-metals. Right, so there's no difference if they're the same. That leads to the no difference in electronegativity. So if I have hydrogen with one valence electron and another hydrogen with another valence electron, right, and so now that's where they're going to share those unpaired electrons, right, and there's the sharing that happens between those two. So hydrogen's electronegativity value according to table S is 2.1. The other one is also 2.1. So then when you subtract those two numbers to get the electronegativity difference, our electronegativity difference is 0. So then we say that's an equal share. So equal or not different, right? So it's not different, right? So it's going to be not polar, non-polar, right? So that's a non-polar covalent bond. All of our diatomic elements are going to be non-polar covalent bonds. And if you need some help remembering the diatomic elements, there's a couple ways to remember it. I like to say Brinkelhoff. And I know Mrs. Mittiga likes to say Hoff-Brinkel. Or you can do, these are not sevens, these are two, that's a 2. Or you can do 7 up. There's 7 of them. They form a 7, the shape of a number 7 on the periodic table. So if we look over here at my periodic table, nitrogen, oxygen, fluorine, and then down here to iodine, right? So it forms the number 7. And then when I say 7 up, up makes the hydrogen because it's up on the upper part of the screen. So then that is a non-polar covalent bond. So let's take a look at an example of hydrogen sulfide. So a hydrogen with its 1 valence electron, and sulfur has, I believe, 6 valence electrons. Yep, so we'll get those 6 in there. So then sulfur has 1, so this is why it takes 2 hydrogens for every 1 sulfur, because sulfur has to make another partnership over here on that right-hand side. So then we need another hydrogen over there. And so then there's that other hydrogen gap over there. So we have 2 hydrogens and 1 sulfur. So we have 2 bonds between, and they're between sulfur and hydrogen. Sulfur's electronegativity value is a 2.6 and hydrogen is a 2.1. So then this electronegativity difference is only a 0.5. So that's their electronegativity difference. This would be slightly polar. If we compare that to our HCl that we did on the previous page, that's going to be the hydrochloric acid. The HCl is more polar, right? So HCl would be more polar. The HCl bond would be more polar than this H2S because the electronegativity difference is higher. So in order to figure out if something is most polar or least polar, anytime you see the most or least, right? I'm just going to jot that down here, most, least. You want to subtract your electronegativity difference. You want to make sure you get those electronegativity values from table S. So from our electronegativity difference, right? So as we go, that startled me for a second, wasn't expecting the noise. As we go from a 0 to a 4.0, because that's the scale is up to a 4.0 electronegativity, the nonpolar, right, meaning not different or the same, right? So this is going to be basically 2 of the same non-metals. And anything like around above 0.5, right, these are nonpolar or very slightly polar. And here we have in our little like just above 0.5, let's say 0.7, all the way up over here to, you know, around 2, let's say 1.7, around that. We call these polar and then bonds. And then generally these are going to be 2 different nonmetals. So as you get higher up in chemistry, if you're in honors chemistry or when you go on to like superchemistry or college chemistry, you're really going to use more of the electronegativity difference in order to say whether something is polar or nonpolar. But at the Regents level, you can pretty much guarantee that if you have 2 of the same nonmetals, because they have the equal electronegativity value, there's going to be nonpolar. If you have 2 different nonmetals, you're going to be polar, and you're very rarely going to get asked anything that's really close together. So now what about from 2.0 to 4? Right, so here we have our nonmetals and nonmetals. These are what we would call extremely polar. And so we call those ionic, which is no longer a share. Remember, this is a transfer of electrons. And I like to remember is TIC. Transfer, ionic, covalent, share. All right, and we have 2 different kinds of shares. We have what we over here, we can call these an equal share. And over here we call an unequal share, right? Because they are different, one stronger than the other. And then here we have the transfer, not even a share. And so whenever we have these ones that are polar, we're going to have a delta positive and a delta negative end. The one that is the delta negative end is going to be whichever element has the higher electronegativity value. So let's see what we have on our next slide. Right, and here we have our transfer, which is going to be between metals and nonmetals. All right, then I think that's where we're going to stop for today. So again, quick review. We have a polar bond is between 2 different nonmetals because it has a larger electronegativity difference. One element pulls the electrons more than the other, creating this partial negative and partial positive ends, right? So that's why we use this lowercase Greek letter delta. And then we have our nonpolar bonds, which are basically between 2 of the same nonmetals that have an equal share of electrons because they have almost an equal electronegativity difference. All right, until our next video. See you then.